What's up, guys? Welcome back to ONeill Code. Let's say you're asked the following question. Given a linked list, remove the nth node from the end of a list and return its head. You will be given two parameters, one being n and the other being the linked list you are trying to remove from. In this video, I will be going over a brute force solution to get you started and then optimize it using two runners to get a much more efficient answer. So let's dive into this by first looking at a linked list. I'll give an example here with a linked list size 7. When you get a linked list, you actually won't know the size of it because you'll only be given the head of the list. This will be the main obstacle of the problem. How can we optimize this to make it as efficient as possible if the linked list is a singly linked list? Just as a note, a singly linked list just means you can only move forward and not backwards. So the data structure will include a next but not a previous. But anyway, let's look at the brute force solution. It's pretty simple. We just need to find the length of the linked list. We do this by iterating through the whole list until a node's next is equal to null. This means there's nowhere else for it to go from there. Once you get the length, iterate again through the list, but this time only length minus n minus 1 iterations. This will get you to the position right before the node you are looking for. Once you are there, you can just connect that node with the node 2 places in front of it, removing the correct node. So there we go, we have our first answer. As you can see, it took us 9 iterations in this example. It doesn't seem like much, but let's say instead of length 7, it was 7,000. That means we iterate through an extra 3,000 nodes to find our answer because of the second pass through. So how can we do this in one pass through of the linked list? Well, the first thing we need to do is look at n. We want to be n minus 1 positions behind the length of the linked list to remove the node. So what if we use 2 runners instead of 1? This means that we just have 2 pointers to the head to start off. Then we can move 1 runner n plus 1 positions in the linked list. Once it gets there, we know the second runner is right where we want it to be. If we move both runners now at the same time, checking if the fast runner hits a null next, we'll find our placement. This is sometimes called the fast-slow technique. Have one runner moving ahead of the other to complete the objective. The slow runner will be n minus 1 positions behind, and we can skip the nth node just like we did in the other example. And we did this all in one pass through. And again, we have the answer. We can just return the head of the linked list and we are done. Now, if you look at the 2 different iteration counts, it is 33% faster in this particular example to do the 2 runner method. And that percentage will be greater or smaller depending on the n that is given to you as a parameter, but that is a huge difference. So now that you know the optimized algorithm, let's get it going in a Java example. Alright, so before we get started with this example, let's look at some helper functions I created to better demonstrate this problem. So we have a generate linked list that's going to take in a length, it's going to get random numbers 1 through 10, give it to each node, and then return the head. Then we have a print linked list that's just going to basically print out what it looks like down here. It's going to have a node and then point to its next. Then we have the actual node, a list node. It has a val, it has a next, and then it has a constructor that takes in an int and gives it to the value of the node. So those are what we're going to be using in this example. And this is what it looks like to generate the linked list. It has random numbers each time. So let's look at the actual method we're going to be creating. So let's think of some edge cases that we can knock off right off the bat. So if you are given a head that is null, we know that we just need to return null. So we can do if head equals null, return null. Another one we can do is or if head.next equals null. We can do this because if you're given a length 1, you'll only have a head. And if you're trying to remove the head, that means the next would be null. So you're going to return a null. So if you remove the head, there's going to be nothing left, and you're going to return null. So let's go back to our example of 7. The first thing we did was we created a slow and a fast that pointed to the head of the linked list. So we do list node slow equals head, fast equals head. We now have a fast and slow pointing to the head of the linked list. Now the next thing we did was we moved fast n plus 1 positions in front of slow. So if we do for
int I equal 0, I is less than or equal to n plus 1, I plus plus. Now we're just going to move fast by doing this. Fast equals fast next. You're just going to go through it n plus 1 times until fast is n plus 1 positions in front of slow. Once it gets there, we can move both fast and slow at the same time. So if we do while fast does not equal null, all this is going to do is make sure that the fast goes into the end of the linked list until the next equals null, or until fast equals null. So while it's doing that, we can just do slow equals slow.next, and fast equals fast.next. So now we're moving both at the same time through the linked list. So once fast gets to the end, slow is going to be n plus 1 positions behind. So in this example, we're giving it 2. So this is the node that we're trying to remove. Slow is going to be here at the 9. Then we just need to skip over this 7 so that 9 is pointing straight to the 2. So basically, we're going to take 9's next, which is 7, and point to its next, which is 2. So if we do slow.next equals slow.next, we're going to take out the 7 because 9 is going to be pointing directly to 2. It's going to be pointing to its next. And then lastly, we just need to return the head. So if we do this and then print out the new linked list, let's try it. We are going to have 9 is the one we're removing because it's this n to the last node, and then 3 is going to be pointing to the 10, which exactly happens here. It's skipping over it. So this right here is all you need to do to solve this problem. But there's one more edge case that we need to think of. What if they give us an nth node that is larger than the linked list? So if we try this, we're going to get a null pointer exception. Because here it's going to keep going until it gets to a null next, which you can't do, and it'll give us a null pointer exception right here. So if we check if fast is null before it ever hits that null next, we won't get that. And all we need to do is return the head of the linked list because you're not actually going to remove anything if the n is greater than the length of the linked list. So if we try this, we're going to return the same size linked list, the exact same linked list actually. So there you go. That's all you need to do to solve this problem. You're going to have a fast and slow that points to the head of the linked list. You're going to move fast n plus 1 positions ahead of slow, move them both at the same time, move slow's next all the way to its next. That's how you skip over the node, then just return the head. You have these 2 edge cases you're hitting, and then this last edge case right here. So hopefully that helps you guys. If you have any more questions, just let me know. If you liked the video, please give it a like and subscribe. Thank you.